Hello everyone, I'm Yuwei from the University of Tokyo. Today I'd like to share with you our recent research on blockchain-based federated learning against endpoint adversary data corruption. First, I'm going to present the background of this research, then I will share with you the proposed blockchain-based federated learning, which will be broken down into the two sections: endpoint thread with corrupted local training data, implementation of blockchain strategies in federated learning. Next, I will discuss the evaluation results and finally conclude the presentation. Federated learning has been used to collaboratively train a global model of machine learning with the distributed datasets protecting users' data privacy. However, within a decentralized scheme like this, endpoint threat caused by adversary users can greatly affect the overall performance of the system. We propose the blockchain-based federated learning for elevating the influence of endpoint adversary training data. To begin, I'd like to share with you the traditional federated learning proposed by Google. Instead of uploading local training data to a central server, federated learning allows participants to initialize and train a machine learning model using their local dataset. So uploading parameters of this trained model, the central server conducts the aggregating function to generate a global model for intelligence sharing among participants. This leads me to my next point. We consider a scenario where the participants are collaborating with each other for multi-cluster classification task. This scheme consists of 3 users who train their local convolutional neural network to classify the binary images of handwritten digits from the meanest. One of the 3 users is an adversary who performs an attack on the parameter server by uploading corrupted local parameters, thus affecting the performance of the other users. For each round of learning, the adversary will train the local model with adversary data. Then the aggregation performance purpose at the parameter server incorporates the corrupted parameters into the global model. After the other users download these latest global parameters, the performance of the local model for classification will be impacted due to the malicious upload. For the experiment, we divided the training set with a total of 60,000 images randomly into 3 datasets as a local dataset of a user. To analyze and understand how an endpoint threat will affect the overall performance of the scheme, we adopted 2 methods to generate the corrupted data. First, a method called the salt and pepper noise was used for adding random noise to original data. We generated the images with various degrees of noise and studied the relationship between the noise degree and the overall performance of the scheme. Similarly, we also adopted a method called occlusions using a randomly positioned circle with various diameters. The applied convolutional neural network is a 4-layer convolutional neural network with the following architectures. It consists of 2 convolution layers and 2 fully connected layers. The other hyperparameters we used is shown below. We conducted federated learning for a total of 20 rounds training using this model with the different degrees of noise and occlusion respectively. The next thing I will share with you is the implementation of blockchain strategies in the federated learning. As shown in this graph, for each round's federated learning, the update from a user will first be added to a buffer with other information about the update process. A committee consisting of several members responsible for verifying the update will conduct a consensus. If more than half of the members confirm an update meets all the criteria, it will be added to the blockchain. Especially for the consensus, the committee will conduct a process called the proof of work, where these items will be verified before adding the block to the blockchain. First, if the update of local parameters is qualified for aggregation. Second, if the generated hash of the block is valid and satisfies the difficulty criteria. And finally, if the previous hash stored in the block matches with the hash of the latest block in the blockchain. For evaluating the quality of an update, we conducted the inference of the uploaded local model based on the community's validation dataset, using the accuracy rate as a metric. Then we further computed an adaptive threshold based on the inference result of the latest global model on the standard validation set. As a result, if the score of an update was higher than the threshold, then the update was qualified. Otherwise, it was unqualified and would be removed. Besides the information stored in a block of blockchain for future recovery and tracking, as shown in the graph on the right side, includes information such as the user ID, the update detail, timestamp, the quality of the validation, etc. Now let's take a look at the result. It shows the validation accuracy at each epoch during the federated learning. In this graph, the blue line shows the threshold and the other line shows the users. And one of these users, which show in the orange line, is adversary. As we can see, we successfully identified and removed almost all adversary updates by comparing the threshold and the quality of each user's update. We computed the validation accuracy at each epoch, both for the adding the noise and adding the occlusion situations. And they both show the great performance with respect to different degrees of the corruption. This graph illustrates a comparison with the traditional federated learning. As shown in the graph, with the increase of the data corruption's degree, the proposed blockchain-based federated learning with the consensus process keeps great performance, showing an overall validation accuracy of 0.957 when noise reaches at a degree of 1, compared with the score of 0.9 of the federated learning. Similarly, its reaches at 0.9441 occlusion reaches a diameter of 28 compared with a score of only 0.922 of the federated learning. On the other hand, we can see the traditional federated learning without the consensus shows a decreasing validation accuracy result, where the degree of noise and occlusion keeps increasing. To summarize, we proposed the blockchain-based federated learning against endpoint adversary data. Community consensus allowed the overall validation of a local model update before being further aggregated into the global model. The endpoint data corruption with varying degrees of noise and occlusion added was employed to evaluate the adaptability and robustness of the scheme. Compared with the traditional federated learning, the proposed method showed a more robust inference result for the classification. For the future work, it includes studying the scheme with more participants involved and exploring an efficient method for the community selection. And that brings us to the end of the presentation. I'd like to thank you for your time and attention today. I'll be happy to answer any questions you may have now.